Long time no see. All right, so let's get started. Does the room sound different?
Yes.
Oh, okay.
It's also very hot.
Do you guys want to open the windows? If we can. Might be above my pay level, but I can try. Is that better? Yeah. Better. So, let me try this better? One more. Okay, can everyone see the board okay? Yeah. All right, so right before we broke for spring break, I went over the mechanism of taking a primary amide to a nitrile. And so before spring break, we talked a lot about amide synthesis, ways to make amides, and the dicyclohexyl carbonate imide mechanism. All stuff that is important for chapter 17. And so we're going to finish up chapter 17 and then hopefully start out the very basics of chapter 18 today. So for making an amide, what I showed you guys before spring break, they take an amide and an anhydride, like this is acetic anhydride, and heat. The product we get out is going to be a nitrile, so a carbon with a triple bond to a nitrogen, and 2 equivalents of acetic acid. And the mechanism is basically, first you want to draw both resonance structures of your amide. And what drawing both resonance structures of an amide shows you is that there's a fair bit of partial negative charge on your amide oxygen. So an amide oxygen is a nucleophilic oxygen. It's a surprisingly nucleophilic sp2 oxygen. And so what can happen if you take a good electrolyte, like acetic anhydride, and throw in some heat, the amide carbonyl oxygen can now attack acetic anhydride, giving us our acylated amide at the oxygen. So that's how nucleophilic an oxygen in an amide is. It can act almost as an alcohol and attack an anhydride, giving us this intermediate plus 1 equivalent of acetic acetate. So the conjugate base of acetic acid. And you have this nitrogen with 2 positive charges, with a positive charge and 2 hydrogens. And so this is a quite acidic sp2 nitrogen. This is almost like an aminium. And so this acetate can go and grab the proton to give us this neutral compound here, which has a lone pair of electrons, and can do almost something that's almost reminiscent of an E2 elimination. So parentheses, and we go E2 elimination. So these lone pairs of electrons and the nitrogen can go in and kick up acetate, giving us our protonated nitrile. And then of course, since we kicked up acetate, the acetate can pick up this proton to give us our product. So the net transformation I have highlighted in orange, a primary amide. So an amide where the nitrogen has 2 hydrogens, it only works in that case. Acetic anhydride and heat will give you a nitrile. And it goes through this mechanism involving the oxygen attacking the acylated, and then some proton transfers, and E2-like elimination to give us the triple bond. Yes?
Is it possible for that E2 to be intermolecular?
For the, what, this E2?
Yeah.
To be in, well, this, you mean,
Intramolecular.
isn't this an intramolecular E2, or? Oh, you mean, so, is your question,
without the acid coming back, like, so,
I don't think so.
okay.
I'm actually trying to draw stuff up in my mind, but I think I might be answering a different question, so I don't want to go down that Pandora's box.
All right.
But in general, the E2 will go from, well, this will be an E2 elimination. We start from one molecule and you have two coming out. So why is this useful? How do we, from previous in this class in 232, how would you normally make a nitrile? I know there's a homework question along these lines. How would you normally make a nitrile? Yeah, you do an SN2 with potassium cyanide. So you take some kind of alkyl iodide, plus potassium cyanide, so KCN, some kind of polar aprotic solvent like DMF, because that's what we do for SN2s. And so, and then the nitrile will just do an SN2 reaction, kicking out the iodide. Giving us our nitrile. So our classic SN2. And of course it proceeds to backside attack through the sigma star. So the nitrile, one pair of electrons in the carbon, attacking the sigma star of the carbon, iodine bond, kicking out I minus and giving us our nitrile. So a classic SN2. So this is great if you want to make nitriles on primary or secondary carbons. But what if we wanted to make a nitrile on a tertiary carbon? Could we make this through SN2 chemistry? No. Why can't we make this through SN2 chemistry? It's too hindered, right? SN2s don't work on tertiary carbons. There's too much steric hindrance for the carbon iodine antibonding orbital. So it's drawn here. We have all these methyl groups which are really hindering the antibonding orbital, so the nucleophile can't get to the antibonding orbital, so we have no SN2 reaction. So how do we get around this? Well, we get around it using this chemistry, just to show you an example. So doing a forward synthesis, and this is very similar to a question we have on the last year's exam. So you guys will see this when you guys study for the exam coming up. You take your tertiary halide and magnesium 0 to give you a Grignard. So here's our Grignard. And now we need an electrophile that will put a carboxylic acid in it. And I have this in the notes and it's in the book, but I'll go over it real quickly. A good electrophile to make a carboxylate or a carboxylic acid is CO2. Yes?
Is it supposed to be iodine or bromide?
Oh, good catch. I'm so used to drawing magnesium bromides. So magnesium iodide, same thing though, same thing. And so then what will happen is our Grignard will attack the CO2. Giving us our carboxylate. which we can of course pronate using acid to give us a carboxylic acid. So first off, that's a good way to make carboxylic acids, by taking your Grignard and CO2. It's a great way to make carboxylic acids. So now we've got a carboxylic acid. Now what we can do is now we can make our nitrile. We can make our amide. And we've talked about a million ways to make amides in this class. You can make the acid chloride, the thionyl chloride, and then throw in your amine. Or you can take dicyclohexyl carbodiamide and throw in NH2, NH3 to get your amine, amide. So, we can talk about several ways. And just for review, in the most recent thing, let's do a carbodiamide amide synthesis. And I'll draw DCC in red. So we can take first our carbodiamide, which the carboxylic acid is going to react with to give us an activated and hydride-like transition state we talked about on last Friday before our spring break. And then after we let that stir with the carbodiamide, we can add our amine. So in this case, it will be ammonia, NH3. And through a mechanism we talked about a lot last week before spring break, will give us our primary amide. And then we can just use these conditions, acetic anhydride and heat. And that will give us our tertiary, highly substituted. I'm going to try it like this just so I have more room. That will give our nitrile out. So if we want to make a really, really hindered tertiary nitrile, the secret is via making the amide doing some typical amide synthesis, so forming a carboxylic acid whichever way possible. In this case we used the Grignard and CO2. Then making our amide any way you want to make an amide. In this case I used the carbodiamide and ammonia mechanism, but you can also do thionyl chloride to form the acid chloride and throwing in ammonia to attack the acid chloride to give us our amide. Again, stuff we've talked about a lot before spring break. And then once we get our primary amide, then we can just do our acetic acid and heat, and that gives us our nitrile. And nitriles are really useful synthetic intermediates due to chemistry we've talked about in 232 and 432. So does anyone want to tell me some chemistry we can do with nitriles as a review? We can make ketones. How would we make a ketone out of a nitrile? Well, what would the first step be, though, to make a ketone? Hydrolysis with water we're going to talk about in a few minutes of nitriles. But what happens if you take a nitrile and you throw in LAH or dibol or Grignard? All right, I'm going to take a little bit of a detour real quick. So, review. Nitriles are fairly electrophilic at carbons. So, for example, if you take a nitrile, you take LAH, and this is stuff we talked about in chapter 16. We will get a primary amine out. If you take a nitrile and dibol, we have two options, right? If you take dibol out and add water, get an imine out. And of course we know if you take imines and add H3O and water, we'll hydrolyze the imine and get a carbonyl out. Same idea. If you take Grignards or alkylithiums, except instead of getting imines, aldamines and aldehydes, we'll get ketones and stuff like that. So take an organolithium, it'll add in the nitrile here, giving us, if you just touch with water, an imine base in the ketone. And of course, if you take imines and throw in H3O, you get the carbonyl out through the imine hydrolysis mechanism we've also talked about a lot. So in general, nitriles are electrophilic. You can treat them a lot like carbonyls. When you add a strong nucleophile into the nitrile, it will initially give you an amine, but then you can do a amine hydrolysis mechanism or an acetylate type mechanism to get back to the carbonyl. So all stuff that was covered on exam 2. So nitriles are really useful synthetic intermediates. So let me show you 2 more reactions for nitriles to add to this menagerie of things. So far we know nitriles, LAH, give us the amine. Nitriles, dibol, imine, if you add H3O with dibol, aldehyde. Grignard nitrile, secondary imine, if you add H3O, imine hydrolyzes to give us our carbonyl. Through the acetyl mechanism we've talked about a lot. I'm not going over the mechanism now because I'm going to go over the mechanism in a different context right now. So we know strong nucleophiles is going to add in the nitriles. Under acidic conditions, we can have water added in the nitriles to give carboxylic acids. And we can also, under basic conditions, have hydroxide. And in the nitriles to give us carboxylates. So this is not too different than any of these reactions. Since nitriles can be electrophilic just like a carbonyl can. It's a sp bond instead of an sp2, but it's an sp bond with between a carbon and the more electronegative nitrogen. So you can guess there's going to be a fair bit of partial positive charge at this carbon. So think of nitriles a lot like carbonyls. And so the acidic mechanism starts out with a brief deprotonation of nitrile. Of course, the equilibrium is going to favor the neutral nitrile, but under this chemistry, everything's in equilibrium. We can funnel through intermediates like this. And it's particularly important to be able, under acidic conditions, to protonate this nitrile because then water can attack it. gives an intermediate like this. And so I hope you guys are starting to see this is not that different than the acetal imine hydrolysis mechanism. So then we have a proton transfer. It's our rate to draw them inter or intramolecularly in this case. I'll draw it intermolecularly. How do I compete with that? So that gives us an intermediate like this. I know we can draw the mechanism, because now this is a nitrogen with a positive charge after it. So let's switch to double bonds between the oxygen and the carbon rather than the nitrogen and the carbon. And that gives us something that looks like this. So a protonated carbonyl. From this class, what do we know about protonated carbonyls? They're really electrophilic. So now water can add in. And I hope you guys are drawing the parallel between this mechanism and, let's say, a Fischer esterification, or an acetal mechanism, or one of the numerous conditions we've gotten over time and time again. Because this is really just a slight variation of a mechanism we've really been focusing on for the last few days. Or really the last few weeks. And so water adds the protonated carbonyl. We get this. Another proton transfer. Now that gives us this ammonium intermediate. And if you form ammonium, we know we can kick it off as a good leaving group. And that's going to give us a protonated carboxylic acid plus ammonia. But from pKa concerns, we know the ammonia is going to quickly grab that proton to give us our product. It seems complicated, I know, but it's just a bunch of things we've talked about time and time again in this class. So I hope you guys don't freak out too much, because again, this is protonating some kind of carbonyl type thing, water adding in to cation a protonated carbonyl type thing, a couple proton transfers, draw a couple resonance structures. Oh, that gives us another protonated carbonyl type thing. Water adds in the protonated carbonyl type things, because in this class, that's what happens to protonated carbonyl type things. Water adds, giving us this thing that looks just like an acetal. And then it just collapses into the acetal mechanism we've talked about so much. Where we have some proton transfers, we kick off something, a good leaving group like an ammonium, and we get our product. Of course, under acidic conditions, we expect the carboxylic acid to be a carboxylic acid. Is that okay? Is that something raising your hand?
Oh,
Yeah.
I'm thinking that the answer is productive pathway, but
Yeah.
just with the reasoning being of electrons being on the nitrogen and that being less
Right,
electron rich.
So you're saying in this case, so are you talking about this step in particular?
One where the equilibrium is, I was just,
Oh, you mean
Yeah.
this case?
yeah.
Oh, resonance structures.
Okay, so.
These two are just resonance structures, so really think of it as a resonance hybrid, not a particular one of those. But as far as this is concerned, you know, yeah, the positive charge would prefer to be on the nitrogen, right?
Yeah.
So you could have water add into this intermediate and go to here pretty quickly, right? It's the same thing. Pedagogically speaking, I was trying to draw an analogy between what we've seen time and again.
Yeah, no,
But yeah, no, it's probably more correct to have it go into this resonance structure, but same difference. I don't really mind which one, but good eye. That's a really good question. I'd like to hear. All right, so under acidic conditions, we can hydrolyze a nitrile to a carboxylic acid. Conversely, under basic conditions, we can hydrolyze a nitrile into a carboxylate. This mechanism, I think, will be a little bit quicker, and it's nothing. This is going to be very similar to the mechanism of the hydrolysis of an imine. So again, you've seen this mechanism before. So first step, with sodium hydroxide and heat, we don't need any activation with sodium hydroxide and heat. Sodium hydroxide is a pretty good nucleophile as is. So first step is sodium hydroxide, just adding into that. Giving us this. Sodium's probably going to be a counterion here. You can now imagine a proton transfer. Again, inter or intramolecular proton transfers are fine. It's whatever you feel most comfortable with. In general, most times intramolecular proton transfers are fine, but every time inter are fine. So intermolecular proton transfers, having a solvent do it, assuming the pKa is right, will always be correct. Whereas intra, kind of like what I've been drawing a lot, those are correct most of the time, but we realize there are sometimes when they might not be correct. So I know some of the TAs, like Tim Montgomery, like to tell students during his office hours, you'll always safe with the intra, or with the intermolecular transfer, whereas with the intra, you have to know what you're talking about. Anyway, in this case, pKa-wise, I think it's fair to say that the nitrogen with the minus charge can be basic enough to take this proton. So we can get this. We're in water, right? We are in water. So we can imagine the ability to protonate this. To give us our neutral species. Now again, we're water and heat. So hydroxide can now add into the double bond. And in this case, you can draw either tautomer. And you know what? I'm going to be consistent with what I did here. And I'm going to draw the tautomer just to be consistent. But I think this one will be more clear. So what I'm drawing now is a tautomer. And tautomers are similar to resonance structures. It's just a proton moves. And so I'm going to draw it stepwise. first off, we can draw a resonance structure. Can everyone see this okay? I just realized I'm kind of small. Alright, so this is what I did here was I just drew a resonance structure where the carbon electron density was kicking down, putting the minus charge now on the nitrogen. Oh, putting a minus charge on the nitrogen. And then if you draw this resonance structure, it almost makes sense for this nitrogen with the minus charge to grab the proton from the oxygen with the positive charge. Let me see if I can. Is that better? Yeah. All right. So we have this proton transfer now. Giving us now a neutral atom. So pretty much the first step, all of this stuff right here, it's just water adding in here and a couple proton transfers to give us a neutral atom. All right? And so this intermediate from water adding and having the first proton transfer right here gives us this neutral compound with one proton and nitrogen, double bond carbon to nitrogen, and one proton and oxygen. And we can draw a resonance structure followed by a proton transfer that gives us what's more recognizable of it as an atom. And so this, and we'll be talking about this more shortly, is what we call a tautomerization. A tautomerization. So again, it's like a resonance structure followed by a proton transfer. And so tautomers are not resonance structures because a bond breaks and moves. But the way to think of to draw a tautomerization is first you draw a resonance structure, and then you move a proton to give you a neutral compound. And then the first compound and the last compound are now what we call tautomers. And hopefully I can do that justice in a second. And so now this gives us an atom. And do you think under basic conditions and heat, we can kick off the amine to give us a carboxylate? This is going to be very similar to a basic hydrolysis of a ester now. And so now just for room, I'm going to start from the amide here, and then talk about the amide hydrolysis under basic conditions and draw the analogies to the ester hydrolysis. All right, again, water attacking a couple proton transfers gives us the amide.